All right, so in the previous session, we went through ROC curve, ROC and AUC curve. So ROC basically tells us what is the optimal threshold for any classification model. And AUC basically denotes the area under the curve. So all in all, it tells which is the model that is working best for my data. Now, here we got this particular graph when we left off the session. And this graph was showing some thresholds and what was the TPR, basically true positive rate, and FPR, false positive rate at these locations. All right. So one thing that we need to know from this data is that since we are talking about optimal threshold, so we need to find out which is the optimal threshold for this case. Now I told you that ideally the true positive rate should be 1 and the false positive rate should be 0. So whichever threshold is closest to 0, comma 1 coordinate, that is the ideal threshold. So can you please look at the data and give me any answer? Basically, can you guess which is the optimal threshold in this case? Any guesses for the optimal threshold in this case? 0.84. Okay, here I haven't highlighted a 0.84 threshold among the highlighted ones. Okay, your value might not be exactly correct, but whatever you feel that nearer to this threshold, the optimal threshold might lie. So tell me among these threshold, which is the nearest to 1 comma 0 comma 1 coordinate. Okay, 0.25 according to Mothers. Anyone else wants to miss? Chalo, no worries. See, when we look at the graph, it might we might have some difficulties in identifying which is the true optimal threshold for this particular data. Like I can see that this part of the curve, basically this part, it is closer to this point. Okay, this is my ideal threshold point. So I need to find where is the optimal threshold, but it is going to lie somewhere around this data. So we can write a piece of code to identify it. So we have true positive rate and we have false positive rate. Okay. So if I subtract true positive rate from false positive rate, this is the data that I get. And if you can see, if you subtract for this point, if you subtract true positive rate from false positive rate, we'll get the result would be 1. Okay. Which means that if I perform this subtraction and if I get some data, then wherever the data okay, is largest, that particular point is my optimal threshold. Why? Because we can see that for our ideal threshold, the subtraction between true positive rate and false positive rate is equal to 1. So if for my data that I have, if I subtract true positive rate from FPR, I'll get an array of values. And wherever in this array, the value is maximum, that particular point is my optimal threshold point. So what we can do, we can pass this data to a function that is called argmax. Now what the argmax function does, it is going to return the index position of the greatest number that is present in this array. Okay, so we got 42. Now what we can do, we have a list of thresholds that we had defined above. Basically this, and here if we index out threshold present at the 42 position, It says 0.2. Someone's mic is on. Can you guys please look into it? Yeah. So according to this particular data, we get to know that at 42nd index, the value which is present, it is 0.24 for threshold, which means this is my ideal threshold. Okay, for this particular data. Do you guys get it? Why this is the ideal threshold and why we are able to find it in this manner? Not the ideal one, the optimal one for this data. Okay. Now, just to wrap up our CNA, we going to try one more thing, and that is we are going to compare two models, two classification models that out of both models, which one is working best for this particular data. So from SK learn dot one sample, I'm going to import random forest sequential. And I believe we have already splitted the data. The top here, we have it. So simply pass your explain this movie. This is random forest and it is not fixed. As of now, I'm not passing any model parameters. Still, I'll be able to create the model because you can see that we have default parameter values. Okay, so here the estimator is 100 and criteria is Gini for this particular step. Now let me just train, fit the data for extrain and writing. This is the fitting level, and once I have fitted it, I am going to calculate the probabilities. So for RF, predict probe A, this is the function, and here we are going to pass out the data. So let me check. We were passing X test, I think. Yeah, X test. So let's slice this part out. Alright. So these are the probabilities that we got, and let's call them RF probabilities. Now it's time to create the RFC for this particular data. So I'm going to get the values. We'll use the RFC prop function. We'll provide the y test, and we will also provide the probabilities that we got. And we know that it will return three values. So false positive rate for the random forest, true positive rate for the random forest, and thresholds for the random forest. This is the same trend. Okay. Earlier, I created this logistic regression model, and this is the same thing that I did over here. You can see. Then I use these values to plot this curve. So I'm going to copy the above code, and I'll simply make changes to the channel. Let's do this. Yeah. So this is the plot that we created in the session before. This one was for logistic regression. All right. And this part of the trace was with respect to the different thresholds that we were aiming to highlight in the graph. So I'll make one change that instead of saying RC curve, I'll say logistic regression because this one it is for the logistic regression model. And here I copy this part and I'll change this one. Why am I changing trace one? Because I don't require to highlight the thresholds. I don't want to highlight the thresholds for this particular graph. I simply want to show how the curve is different for logistic regression and for random forest. This one is for random forest. Okay. And here we will change the value. So instead of saying logistic regression, let's say random forest. And here instead of providing FPR and TPR, because these values, they belong to the false positive rate for logistic regression and true positive rate for logistic regression. So we'll provide these values that we calculated. FPR for random forest and TPR for random forest. All right. We have passed the data, which is for uh, trace 0 and trace 1. And if you want, you can also add area here. We know that if you want to calculate area, so ROC AMC score is the function that we use. And area under the curve, it can be calculated by simplifying it by this and RF quantity. So 81.3 is the area under the curve for random forest. So I'll call it RF AMC. And let's recall what was for the logistic regression one. So I need to go at the top for that. Let's mention it right here. So ROC, AOC, and this 0.832, it is the score that I'm getting from logistic regression. So logistic regression AOC. Now just by looking at this number, okay, I am able to understand that the logistic regression one, okay, the model that is created using logistic regression, it is working slightly better than the random forest model for this data. Okay, so area under the curve for whatever model it is maximum, that model is working best for the data. So one thing you guys can do, if you want to show it on the plot as well, so here we mention area, and you guys can write an F string over here. So instead of mentioning just the logistic regression, we are also going to write in the script. And you can provide the formatting as well. So only till 2 decimal places I want to see the score. Similarly, you can do for random forest as well. This is random forest or F meaning C. And let's convert it into an F string and yeah. Okay. So this is the graph that we see. Let me just zoom out a bit. You can see the red line is for random forest and the blue line is denoting logistic regression. If you had any third model as well, let's say you want to compare decision tree also, whether decision tree works best for this data or not in comparison to logistic regression or random forest. So you can add as many models as you want, and you can basically plot the ROC curve for it. But this limitation for this, sorry, not the limitation, this demonstration that you have over here for different models, you can use the same demonstration for similar models as well. What do I mean by similar models? Now, you know that there are various parameters for random forest and for every classification model. So if you change the parameters, the performance of the model will change. We know that. Okay. If the performance is changing, the model, it might perform better or worse as compared to the previous model. So you can basically construct graphs for a same model, let's say for random forest, but with different values. Let's say I have created, here we have random forest where they are right here. So this one, it takes a default value where there are 100 estimators and there are, the criteria is Gini and max depth and everything else is less. But if you want to create a separate model where you provide, let's say, 200 estimators and you make the criteria entropy, so that model it is going to perform, okay, slightly different from this one. It might be better, it might be worse depending upon the data. So if you want to plot random forest, the difference between these two models, you can again use ROC for that matter. All right, please give a thumbs up if you guys understand what ROC and AUC are, and you know when to use them, how to get the information from them. All right, let's take a small break then, a short break for 3 minutes, and after that we will study about a new algorithm that is called KNN. All right, a short break for 3 minutes, and then we'll meet again. Alright, do we have everyone here? Please give a thumbs up if you guys are playing. Alright, let's talk about a new algorithm. So this algorithm of supervised learning is called KNN. Now, what does KNN mean? It simply means K nearest neighbor. So basically, this algorithm it works upon it classifies a new data point based upon which class is the most near class to that particular data point. To summarize it in a way, let's say we have this data. And you guys are very well aware about the data point or the data analyst. So I'm going to take example for that data only. All right. So let's say we have this data, and this data it belongs to the iris data set. So if you guys can recall that particular data set, it has three values for species: versicolor, virginica, and setosa. Let's say that these flowers they belong to setosa, these belongs to virginica, and this is the versicolor class. Now, if you can recall this data set, you will also be able to recall that based upon sepal length and petal length. Okay, when we took the example of decision tree, we were able to segregate these flowers into three classes. Can you all recall that? When I taught you about decision tree based upon sepal length and petal length, we were able to segregate these three flowers into three classes. Okay, so let's say this graph is for sepal length versus petal length only. And based upon that, we brought the data point, and this is the graph that we got. So what we want to find out here, okay, so let's say we have a new data point. Okay, so this is the new data point. And since we are talking about classification, so I want to classify this new data point into one of the classes. I want to figure out which to which class out of these three this data point belongs. So can you guys guess that if I want to assign one class to this data or new data point, which class should it be? Any idea? Just look at the data and tell me that if this is the new data point and I want to, okay, okay, Virginica. And how do you guys conclude that? How do you guys conclude that I should be assigning it to Virginica? Yeah, because it is nearby. So since this is this new data point, it is much nearer to this Virginica class than it is to Setosa or to versicolor. So this particular data point, it might also have, not might, it will be having petal length and sepal length very much similar to this class. Okay. So just like this, okay, what you guys did, you checked that which is the class that is nearer to the data point. In the same manner, KNN performs. Okay. So what do we mean by this algorithm? So as the name suggests, it is K nearest neighbor. Now, what do we mean by K here? Okay, so K can be anything. It can be any number. Okay, integer basically. So generally the value of K, it is suggested to be between like 3 to 7. Okay, basically everywhere you'll see this algorithm, you'll find the value between 3 to 7. But it can be anything. Okay, K can be 20, K can be 100, K can be 1. And depending upon the value of k, let's say I start this algorithm and I start it with value of k equals to 1. Now, what does this mean? That whichever is my new data point, I'm going to check which is the one point that is nearest to this data point. And let's say I find out that this particular data point over here, okay, this one, it is nearest to this new data point. So what do? I classify this to Vajanika case. But tell me, is it a good practice to basically put the value of k equals to 1 in this case and just classify the new data point to this class just based upon one data point? Is it a good practice? What do you guys think? Why this is not a good practice? Anji Modraj, why do you believe this is not a good practice?
Uh, because it was a single point, not a cloud of points. So, with the help of only a single point, we cannot classify that this is Virginica class, right? So, for example, there the black dot we were comparing with only one dot from the Virginica, or 1 point from the Virginica. So, only 1 point cannot define the classes.
Yeah, definitely. So if we modify this data and if this was not our real data, and let's say this was the data. Okay, so a data point for the Setosa class was also lying here. But in this case, you very well know that this point, it might be an outlier. And let's say if I was running this algorithm for the value of k equals to 1. So in this case, let's assume that as compared to this particular data point, the new data point, it is nearer to this outlier. So that would be classified to what this Setosa class. Because we were considering only one point, and that point, it turned out to be an outlier. So we shouldn't be relying on the value of k equals to 1 always, because that is just not a good practice. Just relying on one year data point and classifying, predicting the class of the new data point, this is not a good practice. So you can either take value of k equals to 2, or let's say we are taking value of k equals to 3 now. So now what it is going to consider the three data points which are very near to it. Let's say one of them is this one, then this one, and then we have this data point. So it is going to check which are the three nearest data points to the new data point. It is going to measure the distance and the maximum near data points. Okay, here they belong to Virginia class. So this data point, despite being closer to the outlier of Setosa, is classified to Virginia. Because we are not relying only on one data point this time. We took the liberty of measure the distance between three nearer points. Okay, so you can go for 3, you can go for 5. That is completely your choice. Just don't go for one or a very less values. Now, there is no particular method that would tell me which is the optimal value. This is simply a hit and trial manner. So you try with a bunch of values. If it works for you, well, good. If does not work, then change the value of k, try the algorithm again. All right. So talking about this is how the algorithm was performing when the value of k was very less. Okay. Let's say now k is very high. Let's say it is 50. Okay. Now let me just erase these marks. Yeah. So the value of k is very high. It is 50. Generally, it is recommended that you shouldn't go with that much high value, but we are considering it. K equals to 50, right? So let's consider that this Virginica class, it has 30 points. Okay. And this particular class, it has 40 points. And this class, it has 20 points. Okay, I'm considering it, just taking a value. Let's not take 20 because, yeah, let's say these are 35 data points for this class. And what I want to do for this particular new data point, I want to check which are the nearest 50 data points. So for this particular value of k, I know that all the data points of Virginica class will be considered. Okay. But since there are only 30 data points belonging to this class, okay, and my quota is that k equals to 15, so it is going to now check for other data points as well. Let's say it also considers these data points. Okay, so what I'm trying to say here is that if your class, okay, ideally this particular data point, it should belong to class Virginica. We know that. But if the target class, it has very less number of data points, then automatically it is going to consider the nearest data points from the other classes. And let's say that the data points, okay, right now, majority of data points that are nearer to it, they belong to Setosa. Okay, since Virginica does not have enough data points, it would be better if I lower down the data points for Virginica further. Let's say we have only 15. Okay, now this seems a little bit realistic. So 15 data points for this Virginica class and then 40 for Setosa. And since the quota is 50, so even after considering all these near points, it has to consider, it is bound to consider these data points as well. And if the value of k is even further, so it would have to consider the data points from versicolor as well, since they are nearer to it. Okay, and since all the nearer points are exhausted. So in this case, despite the data point being closer to this Virginica class, it is going to get classified for Setosa. Why? Because the value of k is very high and Virginica class, it does not have enough samples. And whenever classifying a point, the KNN algorithm, it checks that the maximum near points, they belong to whichever class that is going to be the class of my new data. Okay, so this is a shortcoming, which is basically if the value of k is very low or it is very high, the algorithm won't be performing like much better or very well on the data. All right, so now let's see what are our takeaways from this particular algorithm. We have basic understanding of what KNN is and how does it work. And it works quite similar to how we were thinking of classifying this particular data. So the takeaways are that k near or nearest neighbor, it works for the value of k and it could be anything. However, you need to check for some values and you need to figure out what should be the ideal value of k for your algorithm. Now, another thing that it does not make any assumption. What do we mean by assumptions? Assumption means that you need to provide some kind of parameters, okay, in order for this model to run. However, KNN, it is non-parametric, which means that you simply provide the value of K and the algorithm is going to work. So it does not make any underlying assumption. You'll be uh, coming across an algorithm that is called a name base. And you'll see that this algorithm, it makes some assumptions on the data before classifying it. So KNN is not like naive base, it does not make any assumptions. It is also called lazy learner. Now you'll come across various such terminologies such as lazy learner, weak learner, strong learner. So KNN is a lazy learner. What do we mean by lazy learner? It does not learn anything during the training phase. It simply memorizes all the details. All right. And whenever it gets the new data, it is going to classify that data point after basically uh, no learning happens during training phase, and whatever conclusion it makes, they are made once it gets the new data point. And based upon the similarity, it is going to classify. And you can basically conclude about it that it is lazy learner just by looking at the data. So if I like remove this data point for which we were running the KNN algorithm, and these are the classes that we have, okay, different classes for the iris bar. Now, ideally, this is my whole data, and this is the data that is fed to the model during the training flow, right? But is there any kind of learning, okay, any important learning that KNN can do based upon this data? It simply has the data points. No, nothing, no new information apart from that. And once it is given this new data point, only then it is going to check whether this is like nearer to any of the data points or not. So the algorithm, it does nothing during the training phase. It simply memorizes stuff, and however it wants to classify the new data point, it does it when it gets the new data point. So such an algorithm is called lazy learner, basically the algorithm which does nothing during training phase. All right. So these are few of the important things that you guys should remember regarding KNN algorithm. Now, here are some advantages and disadvantages that I want to talk about before we wrap up. So, can you guys think of any advantage? You have studied about 3 to 4 algorithms now, and I can assure that you might have found KNN very easy to understand. So, can you think of any particular advantage for this algorithm? Okay, Mordred says less memory consumption. So the main advantage of KNN is that it is going to work very well on large data. I won't say very well it will be working, but it is going to be very effective on large data. Why? Because no learning happens during the training phase. And since no learning happens, training will be faster for larger data, and then the classification will be done. Second, most important thing about KNN is that it is very simple to implement. No tough mathematics is involved. You simply need to measure the distance between the points, and yeah, that's it, nothing else. When we talk about disadvantages, the disadvantage include that we have to define the value of, and it can be tricky, right? Even in this data, we like tried with bunch of values, k equals to 1, 2, 3, and then 50. So consider a data that is consider any real-time data. So it is going to take lots of time and lots of efforts to define this value of, and the whole algorithm it depends on this value. The computation cost is very high. What do I mean by this? Since we are measuring the distance between each and every point with respect to the new data point, so this is going to result into a higher computation cost. So these are few of the advantages and disadvantages of KNN. All right. Now I'm going to wrap up all the introductory part for KNN, and I simply want to discuss few of the distance matrices with you guys. Now, what are these distance matrices? Basically, if we have two data points, since we are talking about measuring distance here, let's say this is x1, y1, and this is x2, y2, and you want to measure this distance. Can you tell me, okay, if you have a little bit knowledge, basic mathematical knowledge, can you tell me how will you measure the distance between these two data points? Any idea? Or like, Modraj has written a formula, and yeah, we can use the same formula to measure the distance. So what I can do x2 minus x1, and I need to square the whole term because this might be negative. And I can do y2 minus y1, again square the whole term because, sorry, and this could be negative as well. And square root the whole term. And this is how you calculate the distance d between these 2 points, A and B. And this particular formula, it is very popularly called Euclidean distance. And by default, if I'm correct, KNN uses this formula to calculate the distance between two data points. A slight modification to this formula could be x2 minus x1 and mod of this term, and y2 minus y1 and mod of this term. This can be also used to calculate the distance between A and B. And this is called Manhattan. We have a similar matrix. So we have Minkowski and we have Haber sign. However, this is used to calculate the distance between two latitudes or longitudes. So there are several matrices that are used. Very popularly, Euclidean is used, but you can also use Manhattan and Minkowski. If you want to use them, there is no extra step that is involved. You simply need to define these in the model, and your model will be trained. Sorry, your model will be fitted based upon these matrices, whatever matrix that you choose. Okay, so this Euclidean one, it is quite simple to understand, very effective, and by default, this matrix is used. All right, so I believe everyone has a clear idea about what KNN is, and I think that you guys find it very much easier as compared to the other algorithms that we have discussed. Am I right? Yeah. Okay, no rigid mathematics involved. Okay, so let's take some time to implement KNN now. Let me just check what is the data that we are using and if I can remove the same. So we have RUC, AUC, and we were using this one as well. Yeah, we can use this one. So I am using the data which involves information about whether someone has diabetes or not based upon their glucose level, blood pressure, skin thickness, insulin, and every other column present in the data. All right, so let me just check the outcome column first. So this is the target column that we have, and I'm going to perform value. Here, when I perform value count, I'm able to observe one very clear thing, and that is that the samples they are not equal. So you can see that the class 0 it has more samples as compared to class 1, right? And I told you that this particular condition it can be cured with the help of a technique that is called SMART. Able to recall its full form. We check. So SMART is called synthetic minority oversampling technique. This is the full form. I also told you guys why we need to oversample or why we need to ensure that both the classes they are equally represented inside our data. Can you tell me why we need to ensure that there is an equal representation? Yes, can anyone tell me why there is an equal why should we make sure that there is equal representation of both the classes? A and N might be misleaded. Okay, so it's just not just about ANN, it's about any algorithm. So whenever you have a data that is not equally represented, the target column is not equally represented. So the model is going to become biased towards class 0 since more samples belong to this class and there is very less representation of class 1. So model is going to favor this class. Because learning would be done majorly for this class as there are more samples. So we need to ensure maybe the model would generate a very high accuracy, but still, in that case, the model would be overfitting. Overfitting as in that it is going to perform best on training data, but not on the testing data or any unseen data. So such a model, it might look like that it is working well, but in general, it won't be working well. The accuracy will be just a facade and it won't be actually accurate. So simply what we need to do, we need to either drop the samples of this class 0 or we need to generate more synthetic samples for this class 1. Dropping the sample is not a good idea because we would be losing data that way. So we perform this SMART technique where we basically create synthetic data samples for a class that is less represented in the target column. And why did I wait for you guys to learn about KNN? Because SMART uses KNN to generate the synthetic data. I cannot simply like duplicate the data and I cannot add it to this class just to make the samples equal. That won't be a correct way. So we use what? We use KNN and like whichever class it is misrepresented, what does KNN do for SMART? It is going to check uh, like if there are two near data points, it is going to create a new synthetic sample between those two data points. So internally, SMART uses KNN to create new data points. So we will be using SMART here to like oversample class 1 and we will be using KNN to generate a model and we'll be like we'll be classifying the data using KNN. So please don't confuse that SMART is always used with KNN only. It is a simple synthetic sample generating technique that can be used with any algorithm, but internally SMART uses KNN to generate the synthetic samples. Please give a thumbs up if this difference is clear to everyone. You guys want me to repeat? It's clear, right? Please give a thumbs up. Okay, then tell me, should I repeat it? KNN is a supervised learning algorithm that can be used to perform classification as well as regression problems. But mostly it is used for classification only. We studied an example for KNN that which involved classifying a new data point to any of the three classes. Got it? That particular algorithm was working on based upon the distance between two data points. So this technique of finding distance between two data points is used to generate synthetic samples by SMOT. Okay. So KNN is an algorithm and SMOT is a technique that uses KNN to generate new samples. I believe it is clearer now to everyone. Okay, so let's oversample class 1. So we are going to import from imvlearn dot oversampling import SMOT. And literally same, we'll be creating an object for small. And just like you ask the data for your model in the same manner, you're going to run this fit resample function and you'll provide X and Y data. So this is generating two things. Again, it is generating X and Y. This is the column, the target column, and let's perform value counts here. Now you can see a clear difference between these things. So let me just remove this particular column. Say, so here earlier I had 500 and 268 samples only, but currently we have both the classes equally represented. So what did KNN do? Sorry, SWOT do here? It generated synthetic samples for class 1. Okay, the samples which were not present but were created based upon the data points of class 1. Okay, so wherever two data points were nearer, a synthetic sample was generated between them. I am also going to mention can use this anything. Okay, so this is done. Now we need to divide the data into train test split and provide X and Y and provide the test size. This will give you X train Y train, X test Y test. Right. Please give a thumbs up if there is no doubt till here. All right, so let's initialize KNN now. So from sklearn dot neighbors, we'll be importing KNN A neighbors classifier. Since this particular algorithm it is used for classification and regression both. So when you are dealing with a regression task, then simply change the name to K neighbors regressor. However, majorly it is used for classification only. So this is the data, this is the model. And if you check the document, you will see n neighbors parameter. By default, the value of n neighbors is service. The metric is Minkowski. If you want to change, you can go to the matrix and here you will find all the value that you can provide. Let me just check. Default is Minkowski to use for distance computation, which results in standard. This. Let me see if it is going to work for Euclidean or not. I'm going to create the model for k neighbors equals to 3. and I'm going to provide the matrix as Euclidean. Okay. So can you provide Euclidean? You can provide Minkowski, you can provide Manhattan, that is your choice. And this is K and N for three neighbors. Let's just fit the data. So K and N dot fit. It's been widely. All right, found input variables with inconsistent number of samples. Let me check what is wrong with extreme. Yeah, the model is fitted now, and we can check the accuracy for it. You want to see the accuracy, you need to import from sklearn for matrix and put accuracy score. And we are going to check the accuracy for widest. Let's get the y predicted as well. KNN3 dot predict x. These are y predict. So I got an accuracy of 75% when I created this KNN model for three neighbors. If you want, you can run this algorithm again. And let's try for five neighbors now. We call it KNN5. And I'll fit the data again on KNN5 and predict. And let's check the accuracy again. You can see a slightly better accuracy with KNN 5. So if value of k is 5, that is working better for this particular data. You can try with a bunch of values. You can go till 6 and 7 and see how if the model accuracy is improving. Again, since you are going to have different models for different value of k, so you can also plot ROC curve for these models and check for yourself which is the model that is working best. Okay, basically visualize the performance of different models. All right, so I believe that you guys understand how to implement KNN now, and it is like much more clearer to you how to use ROC with on different models with KNN. Also, you have some idea about what SMOT is. So if there are any doubts, you guys can ask. Otherwise, we'll end the session for today now.